Chapter 3, Internal Energy and Enthalpy. Section 3.8, Pressure Dependence of Enthalpy of Reaction. In the previous video, we studied the temperature dependence of enthalpy of reaction. The temperature dependence of enthalpy of reaction is usually small because the integral of delta CPM is usually much smaller than the magnitude of the enthalpy of reaction. Therefore, the enthalpy of reaction is approximately a constant within a small temperature range, or even within a moderate temperature range, up to tenths of degrees Celsius. Now, what about the pressure dependence? It's even much smaller than the temperature dependence. The enthalpy of an ideal gas does not depend on pressure at all. The enthalpy of a real gas depends slightly on pressure. If we use Van der Waals equation, we can somehow derive the pressure dependence of the Van der Waals gas approximately. Delta H over delta P under constant temperature condition is Nb minus 2AN over RT. A and B are the Van der Waals parameters. Now we have this delta H is approximately this Nb minus 2AN over RT times delta P. When the pressure changes in an isothermal process, you see this T in the subscript. That means when temperature is held constant, how does enthalpy depend on pressure? Now let's look at one numerical example problem 3.8.1. Estimate the molar enthalpy change for the nitrogen gas given its Van der Waals parameters A and B when the pressure changes from 1 bar to 30 bars. Okay, this is a very significant pressure change, but you will see the molar enthalpy change is very small. Now let's convert A and B to SI units just for convenience. And then we have B minus 2A over RT, which is just this divided by N. We're going to look at the molar enthalpy change. And now we plug in all the numbers in SI units. And then we have negative 7 joule per mole bar as this B minus 2A over RT. And therefore, the molar enthalpy change is B minus 2A over RT times the pressure change, delta P. Delta P is roughly 30 bars. After we do these calculations, we will be able to get this negative 0.2 kilojoule per mole. And this significant pressure change results in only a very small enthalpy change for the real gas. That means if a chemical reaction involves real gases, well, the pressure dependence from the enthalpy change of those real gases can be very, very small. And again, in general, the pressure dependence of a real gas is often very small, even if the pressure change is significant. Now we're going to look at another numerical example to show that the enthalpy of a solid and the enthalpy of liquid does not really depend on the pressure. Well, or you can say the pressure dependence of the enthalpy of a solid or a liquid is negligible. Again, we will change the pressure from 1 bar to 30 bars. This is a significant change. Now let's look at the molar enthalpy change for both ice and liquid water. And then we can estimate the change of the enthalpy of fusion of water when pressure changes. Now first, delta H over delta P is equal to V minus T times delta V over delta T under constant pressure condition. And this equation is correct for all substances. And now this delta V over delta T is simply V times alpha. This is from the definition of alpha. And then we have this expression. Since ice has a density of 0.92 gram per milliliter, we can compute its molar volume. The molar volume is simply the molar mass divided by the density. We get this much. And then delta H over delta P for ice is approximately this much. And we can compute this molar enthalpy change when the pressure changes from 1 bar to 30 bars. You can see this is only 57 joule per mole, or 0.057 kilojoule per mole. Note that the enthalpy of fusion or the enthalpy of chemical reaction, those are usually in like tens of kilojoule per mole, or sometimes even more than 100 kilojoule per mole. So this number is really small. Now let's look at liquid water. We have a molar volume of 18 milliliter per mole, and then we can compute this delta H over delta P, and it's roughly 18 milliliter per mole. Now, what if the pressure changes from 1 bar to 30 bars? How does the molar enthalpy of liquid water change? Well, it's just the molar volume, 18 milliliters over mole, times the pressure change. The result is also very small. It's 0.052 kilojoule per mole. And now, when the pressure changes from 1 bar to 30 bars, the enthalpy of fusion of water is changed by this much. We're going to have the change of liquid water minus the change of the solid. It's only negative 0.005 kilojoule per mole. Now, what's the standard enthalpy of fusion of water at 0 degrees Celsius under 1 bar pressure? It's 6.02 kilojoule per mole. If you raise the pressure to 30 bars, still this enthalpy of fusion is about 6.02 kilojoule per mole. The pressure dependence of a solid or a liquid is negligible. Therefore, the pressure dependence of pretty much all chemical reactions is negligible. Again, in the end, it's just because the pressure dependence of the enthalpy of either a real gas or a solid or a liquid is negligible.